We are looking at a paper today titled Beyond Pixels, From Video Priors to 4D Worlds. And we're just bypassing any preamble today to get straight to the core technical insight.
That's good.
Because this architecture solves a massive, historically expensive bottleneck in 4D generation, explicitly modeling 3D space across time.
Right, which has always been a huge headache.
Exactly. Historically, to generate a dynamic 4D scene, you either had to generate a standard RGB video first and then attempt to reconstruct 4D geometry from those flat pixels.
Which obviously causes catastrophic error propagation.
Or, alternatively, you had to train a native 4D model from scratch, which is just computationally brutal.
Oh, completely.
But this paper completely sidesteps both of those paradigms.
Yeah.
It introduces something called Latent-To-4D.
Yeah, it takes the final denoised VAE latent of a video diffusion model and maps it directly into a 4D decoder.
No pixels involved at all in the translation.
None. And for any ML engineer or researcher listening, the killer application here is zero-shot transfer.
Right.
Because this technique interfaces strictly at the VAE latent level, you can train a single latent-to-4D alignment and refinement network. They call it L4AR.
L4AR, yeah.
And that one trained pathway works across completely different video generative models.
Wait, really? Like entirely different architectures?
Well, whether you're using a text-to-video diffusion transformer or, an image-to-video DIT, as long as they share the same VAE space, the geometry generation just works.
That's wild.
Yeah, the paper demonstrates this using the WAN model family as their testing ground, and they achieve state-of-the-art explicit geometry without retraining the generator.
So, officially, welcome to AI Paper Slop. Our mission for this deep dive is to break down exactly how this latent space bridging actually functions at a mathematical level.
It's fascinating architecture.
We're going to tear apart the L4AR network, examine how it translates fundamentally incompatible tensor grids, dig into the benchmarks, and figure out why decoding AI generations to human-readable RGB is rapidly becoming a liability for spatial computing.
It really represents a fundamental shift in how we define the representation boundaries between distinct generative models.
We're moving away from treating human-viewable formats as the API between neural networks.
Exactly. We don't need pixels to be the API anymore.
Okay, so let's start with the bottleneck. We've established that bypassing RGB is the core innovation here.
Right.
But to actually appreciate the engineering behind the Latent-To-4D architecture, we kind of have to unpack why that RGB decoding step is so damaging to dynamic scene generation in the first place.
Yeah, why is the standard pipeline failing us so badly?
Right, why does it break?
Well, to map out that failure, you have to look at the first of the two existing paradigms, which is that generate then reconstruct method we mentioned.
Okay.
In this pipeline, you have a video generator output a sequence of RGB frames.
Yeah.
Then you feed those flat frames into a completely separate reconstruction model like 4RC or any 4D.
Just to lift them into explicit 4D point maps?
Right. Or maybe a neural radiance field or 3D Gaussian splatting representation. But the fatal flaw here is a severe distribution mismatch.
Because those reconstructors are trained on clean, real-world data, right? Whereas AI video inherently contains structural flaws.
Exactly. The reconstructors expect optically valid, physically grounded images. They expect multi-view consistency because, well, they were trained on actual cameras moving through actual physical space.
Real-world physics.
Yeah. But when you feed them AI-generated RGB frames, those frames contain subtle temporal artifacts, localized hallucinations, inconsistent lighting shifts.
So the reconstructor tries to make geometric mathematical sense of what is essentially an optical illusion.
That is the perfect way to put it. When it tries to triangulate depth from a flickering shadow that literally shouldn't exist, those errors propagate exponentially.
Oh, wow.
You end up with completely unstable, broken geometry. A tiny temporal flicker in a 2D video turns into an object physically shattering into pieces in 3D space.
Right. The analogy I like to use for this generate then reconstruct method is that it's basically like translating a highly precise engineering blueprint into a blurry watercolor painting.
Oh, like that.
And then, handing that watercolor to a construction crew and asking them to build a house based on the brushstrokes.
It's doomed from the start.
You're forcing the system to interpret structural physics through an aesthetic medium that inherently compresses and loses geometric precision.
That perfectly illustrates the loss of fidelity. The generated RGB is the watercolor. It's optimized for human eyeballs, not for a physics engine.
Right. Our eyes gloss over the mistakes, but the math doesn't.
Exactly.
Yeah.
Now, the industry recognized this massive loss of structural integrity, which led to the second paradigm integrated feed-forward generation. Models like 4D Next or World Real fall into this category.
Okay, and how does that differ?
This paradigm makes 4D geometry a native, end-to-end output of the generative process itself.
Which fundamentally sounds like the correct path, right? Just skip the real vector entirely and generate the geometry natively.
It's structurally sound, for sure,
Yeah.
but it introduces a massive operational and economic bottleneck,
Compute costs.
mostly retraining costs. It tightly couples your 4D prediction capability to one highly specific generator architecture.
Oh, I see.
So if a lab releases a brand new, highly capable diffusion transformer tomorrow that understands motion 10 times better, you can't just plug it into your pipeline.
You'd have to execute an incredibly expensive geometry-supervised retraining phase all over again.
Yes, just to adapt that specific new generator for 4D outputs. And that is a huge problem because 4D supervision data, annotated point clouds and multi-view temporal data sets is incredibly scarce compared to the oceans of 2D video data used to train the base models.
So the holy grail for researchers is a reusable adapter.
Right, an interface that skips the watercolor phase entirely but doesn't require retraining your entire 4D pipeline every time a new foundation video model drops.
Which brings us to where this paper finds its leverage. If RGB is a terrible middleman and native end-to-end training is too rigid and expensive, where is the ideal insertion point to extract a 4D scene?
And they found their answer in the architecture of modern DIT families, specifically targeting the VAE latent space.
Okay, break that down for us.
They're essentially exploiting the standardized infrastructure of modern model families. Think about models that share the same variational autoencoder checkpoint.
Like the one family in the paper.
Exactly. You might have one 2.114b, which is a massive 14 billion parameter model trained strictly for text-to-video generation.
Okay.
Then you have one 2.2 I2v, which is trained for image-to-video generation.
Totally different use cases.
Totally different. Even though their upstream conditioning is different and their internal transformer architectures scale differently, they all compress their inputs and decompress their outputs through the exact same VAE.
Meaning their final outputs share the same tensor layout, the same latent normalization techniques?
And the exact same compression conventions.
Yes.
They produce their final denoised latents in a shared common representation space.
So this final denoised latent sits directly upstream of the RGB decoding step.
Right. It hasn't been pushed through the final layer to become pixels yet, but critically, it already contains all the necessary appearance, motion, and spatial conditioning information required to render the scene.
The generative heavy lifting is finished.
Exactly.
So for anyone managing massive training runs, the compute savings here are just obvious. By tapping into this specific layer, the final denoised VAE latent, the researchers keep the video DITs completely frozen. They keep the VAE frozen. They keep the original transformer weights frozen. You're just intercepting the signal right before it hits the RGB decoder.
And because that VAE space is a shared standard across that entire family of models, you can train a single geometry-supervised 4D pathway that serves every compatible video generator.
It acts as a universal translator.
It really does. You have entirely decoupled the 4D supervision from the specific generator's initial training phase.
Okay, but hold on. I have to challenge the actual mechanics of this here.
Sure.
Because intercepting a latent tensor sounds elegant until you actually look at the data structure.
Oh yeah, they're not naturally compatible.
Right. A video latent tensor is a grid of compressed spatiotemporal patches. But a 4D reconstructor requires a highly specific token hierarchy to understand physical geometry.
Very different shapes.
The spatial grids are different, the temporal resolutions don't match, the feature dimensions are completely misaligned. You can't just plug a compressed video latent into a 4D decoder and expect it to output a point map.
No, you definitely can't.
So how does this architecture actually force the translation between these completely incompatible data formats?
Well, that translation is exactly what the L4AR network, the Latent-To-4D Alignment and Refinement Network, was engineered to solve.
Okay, so it's not just a pass-through.
Not at all. L4AR doesn't just pass the data through, it processes it through a rigorous, multi-stage alignment. The first phase is purely mathematical alignment. They start with a fixed trilinear resampling operator.
But trilinear resampling just stretches or squishes the tensor matrix to match the spatiotemporal resolution expected by the 4D hierarchy, right?
Correct.
It changes the shape, but it doesn't change the semantic meaning of the features inside the matrix. How does it learn the actual translation?
You're absolutely right. Resampling just fixes the geometry of the data structure. To handle the semantic translation, they apply a learned 3D convolution across the newly shaped grid.
Okay, so 3D convolution.
Yeah, this looks at time as well as the spatial dimensions. It aggregates local spatiotemporal neighborhoods, allowing neighboring appearance and motion evidence to be mathematically combined.
Interesting.
Then it projects those latent channels into the exact feature dimension the 4D token hierarchy requires.
Wait, but a local 3D convolution only looks at a tiny spatial and temporal window?
Yes, it does.
So if the camera is panning across a complex room, a local kernel has no idea that a chair leg on the left edge of frame 1 is the same physical object moving to the right edge in frame 10.
It has no clue.
So how is a purely local operation establishing consistent 4D geometry across an entire scene?
Well, it isn't. And that's the limitation the researchers recognize right away.
Oh, gotcha.
The 3D convolution is strictly a preparation step to get the data into the right dimensional format. The actual heavy lifting for geometric consistency happens in the next phase, which is spatiotemporal refinement.
Spatiotemporal refinement, okay.
L4AR uses a hierarchical module that alternates between two very specific types of attention mechanisms. First, you have frame-wise attention.
Let's break down how these two interact. Frame-wise attention focuses purely on the spatial structure within a single, isolated frame, correct?
Yes. It reshapes the tokens to isolate the spatial dimensions, completely ignoring time for a moment.
Just looking at the layout of that exact millisecond.
Exactly. It consolidates the dense geometric structure within that specific timestamp, ensuring the spatial relationship between objects in that exact millisecond is coherent.
Okay.
But to understand motion in 3D space, it immediately follows that with global attention.
And what does that do?
This operates across the entire tensor, exchanging information across all spatial locations and all time steps simultaneously.
Okay, so to use a different analogy here, frame-wise, attention is kind of like an illustrator working on a single page of a flip book.
I like where this is going.
They're hyper-focused on making sure the car's wheels are perfectly round and the perspective is correct on that one specific page.
Right.
But global attention is like a film director calculating a continuous tracking shot.
Yes.
The director is ensuring that as the camera moves, the background parallax shifts correctly, and the car's movement makes sense from page 1 all the way to page 50.
That is a highly accurate way to visualize the architecture.
By alternating them, you get the detail of the illustrator with the spatial awareness of the director.
Exactly. The global blocks propagate long-range correspondence and motion cues, solving the exact camera panning issue you mentioned earlier. And the interleaved frame-wise blocks ensure you don't lose the crisp, detailed spatial structure of the objects as that motion occurs. Together, they create a deeply contextualized 4D latent representation.
And once that representation is refined, we just hand it over to the 4D decoder.
Yep. The refined feature hierarchy is fed into a multi-level geometry head. And it's important to note what this outputs. It isn't immediately trying to output a highly complex continuous mesh.
What does it output instead?
It predicts explicit dynamic scene structure on a per-pixel basis. For every single frame and every single pixel, it predicts a metric depth value, a world space rate, which is mathematically defined by an origin point and a unit direction and confidence scores.
So you combine the metric depth, the origin point, and the unit direction, and you generate dynamic point maps expressed in a shared world coordinate system.
Exactly. You have explicit, trackable 4D geometry generated directly from a video latent. And because they established this clean bridge between the VAE latent and the 4D decoder, the training efficiency is something that should make any compute-constrained team take notice.
Yeah, I was looking at the training methodology in the paper, and the resource requirements are just staggeringly low compared to native models.
It's a fraction of the cost.
They train the entire L4AR pathway on only about 1,100 existing reconstruction clips.
Just 1,100.
Most video generation models require millions, if not billions, of video clips to learn structural physics.
But remember, the physics priors, the fundamental understanding of how light, motion, and object permanence work, they're already baked in to the frozen DIT and the frozen VAE.
Right, they don't need to relearn that.
Exactly. The L4AR network doesn't have to learn how a ball bounces. It just has to learn how to translate the latent representation of a bouncing ball into a 4D coordinate system.
And the training pipeline really reflects that. During training, the video DIT is completely offline. They don't run it at all.
Not even a single pass.
They literally just take those 1,100 annotated ground truth videos, encode them through the frozen VAE to get the observed video latents, and use those latents to optimize the L4AR alignment module and the prediction heads against metric 4D annotations.
Then comes the zero-shot inference trick.
Oh, this is the best part.
When you deploy this to actually generate a novel 4D scene, you just swap out the real-world observed latent for a latent generated by the DIT.
And the model doesn't know the difference.
Not at all. Because both latents live in the exact same VAE representation space, the L4AR network processes the generated latent and outputs 4D geometry without ever realizing it's handling synthetic AI data instead of an encoded real-world video.
It's brilliant. But, a theoretical universal translator has to survive contact with reality.
Right. Let's look at the numbers.
Let's dig into the benchmarks. They evaluated this architecture on 2 locked 200K suites, Tex4D 200 and I4D 200.
Yeah.
And they did this using a single L4AR checkpoint. They did not tweak the weights.
One single checkpoint for everything.
They ran one adapter across 12.114B, which is a massive text-to-video model. They ran it on the smaller 12.1.3B, and they ran it on 12.2 I2V, an image-to-video model.
And to explicitly prove the value of bypassing RGB, they performed controlled same latent comparisons.
So comparing apples to apples.
Exactly. They generated a VAE latent. For the baseline, they pushed that latent through the standard RGB decoder to get pixels and ran those pixels through 4RC, which is a top-tier reconstructor.
Okay.
For their method, they routed that exact same latent directly through L4AR.
And the Latent-To-4D method dominated.
Oh, it wasn't even close.
They measured this using projection-based DynoF1. And for anyone unfamiliar, DynoF1 isn't just looking at basic pixel color differences like PSNR might.
No, it's much more sophisticated.
It extracts robust semantic features using a vision transformer. By comparing the dyno features of the rendered 4D views against the ground truth, it measures if the core meaning, shape, and structure of the scene is actually coherent from different angles.
Right, semantic coherence.
On text-to-4D, Latent-To-4D beat the matched RGB cascade by up to 3.45 points. And on image-to-4D, it won by a massive 5.81 points.
And to understand why the gap is so large, you kind of have to look at how the systems handle thin structures.
Thin structures, like what?
Think about a bicycle spoke, or the thin leg of a chair. In an RGB video, if a bicycle spoke is slightly blurry or loses contrast against the background for a single frame, the RGB reconstructor assumes the spoke has ceased to exist.
Oh, and the geometry just shatters.
Right. But in the latent space, the mathematical probability and structural feature of that spoke is still preserved in the high-dimensional data, even as it hasn't been explicitly drawn as a high-contrast pixel yet.
L4AR reads that preserved data and maintains the geometry.
Exactly.
The paper backs this up with human evaluations as well, right? 50 participants viewed cases across the benchmarks, heavily preferring the Latent-To-4D method for geometric plausibility and temporal stability.
Yeah, human eyes preferred it too.
But I want to spend time on a specific diagnostic test the researchers ran, because it answers a critical question about AI hallucinations.
Ah, the sensitivity test.
Yes. The test is called the Grid-Align Null D-DIT Residual Sensitivity Test. Let's unpack the mechanics of what they're actually doing here.
It's a brilliant piece of diagnostic engineering. If you take a latent directly from a generative model, that latent is not going to be perfect.
Right. It's AI generated.
It will contain generative noise residuals that deviate from a perfect real-world encoding. So the question is, does L4AR isolate and handle that underlying generative error better, or is it just masking it?
Okay, so how did they test that?
They isolated a specific DDT-derived residual, basically the mathematical difference between a near-terminal generation step and the final step.
They took this synthetic generative noise and they projected it onto the null space of the L4AR's grid-align module.
Right.
And in linear algebra, a null space is essentially the set of vectors that a mathematical transformation maps to zero. They're basically finding the specific blind spots of the alignment module, mathematically crafting a perturbation that represents typical AI generator noise, and forcefully injecting it into observed video latents to see if the model breaks.
Exactly. They apply this exact same noise to both the RGB decoding baseline and the Latent-To-4D pathway, testing it on the 7 scenes and NRGBD datasets,
which are established, rigorous benchmarks specifically used for testing camera tracking and 3D scene reconstruction in complex, messy indoor environments.
Yes, very tough environments.
And the Latent-To-4D architecture completely absorbed the noise.
It barely registered it.
Across all 30 comparisons, point map drift and camera estimation drift were drastically lower. At a specific perturbation scale, the point map drift for Latent-To-4D was practically negligible around 0.005.
Just incredible stability.
But when that same generative noise was pushed through to RGB pixels, the baseline's error exploded to nearly 0.4.
Because L4AR processes information hierarchically in the latent space, it structurally isolates the generative errors.
Right.
It doesn't force a noisy, uncertain signal into a brittle, absolute pixel representation where the reconstructor will multiply the error across the entire scene.
Taking a step back to look at the ecosystem, this proves that by treating the final denoised VAE latent as the interface, we completely decouple 4D geometry supervision from specific generator training.
Yes, and that decoupling is the future.
We save massive amounts of compute, we stop RGB error propagation at the source, and we build one robust adapter for an entire family of diffusion models.
We really have to seriously evaluate the computational overhead of rendering pixels in AI pipelines moving forward.
It's so wasteful.
We spend staggering amounts of GPU compute generating high-fidelity textures, lighting, and pixel grids, strictly so human eyes can verify the output, only to then ask a secondary AI model to ingest those pixels and reverse engineer the underlying physics.
It is highly inefficient.
By passing high-dimensional latent structures directly between models, we bypass the human-readable bottleneck entirely.
Which leaves you with a final thought to consider as you architect your own systems.
What's that?
If we are successfully bypassing human-viewable pixels to translate AI concepts directly into explicit 4D physics and spatial geometry, are we approaching a point where RGB video is fundamentally a legacy format?
Oh, that's a big question.
Will the native operating system of future spatial computing environments, the physics engines, the generative worlds, the agentic environments, be built entirely in these invisible shared latent spaces,
leaving the literal pixel obsolete for anything other than the final glass display screen?
Exactly.
It suggests a future where models communicate in pure structure rather than aesthetic approximations.
Something to think about as you optimize your own models. Thanks for joining us on this deep dive into Latent-To-4D architecture. We'll catch you next time on AI Paperslop.